From now on, the characterization of the underground utilities will be explained. After we determine the location of utilities, we must know the characteristics of the identified utilities. In this chapter, we will study how utilities can be characterized by various technologies. To characterize a utility using existing utility record is the easiest way to determine basic information about utility. If there is not proper information about the current condition of a utility, most of information about the utility is original utility record. In the utility record, the best situation is there is no replacement or no movement or no repair. But unfortunately, our utility should be managed because it ages as time goes. So the record may be amended as utility section are replaced, moved, repaired, or abandoned. However, the record may be frequently lost, unavailable, or may exclude proper characterization data. So other methods must be available to augment record in determining the characteristic for utility. To deal with this problem, inspection is required, and there is a two inspection method. First, exposed utility inspection, and second is internal inspection. Before full-scale inspection, we can get general information from ownership, type of utility, and usage status. Based on this information, we can estimate the current condition of a utility. Ownership cannot be inferred directly from a physical inspection unless an ownership tagging or identification system was used during construction or repair process. However, ownership can provide general information by providing an ownership tagging or marking. Usually, this tag or mark has colored pipe or colored markers. As well as general characteristics, physical characteristics can also provide important information to characterize underground utilities. There are three categories for determining physical characteristics. First, utility size and material. Second, floor characteristic. And third is age and condition. It is very important to detect these physical characteristics because this information gives a crucial clue for inspection. Therefore, before performing inspection, general and physical characteristics should be identified. Public safety concerns regarding oil and gas pipelines have required the development of improved integrated management programs. These programs aim to prevent structural integrity problems, especially those that damage public safety or business operation or the environment. To operate such a program, the physical condition of a pipeline must be evaluated using various combinations of internal inspection or hydroelastic pressure testing and direct assessment. Another internal inspection method is the crack detection tool. It is the most challenging task among internal inspection technologies because this method is much delicate than other methods. In the first figure, a LED device transmits a ultrasound wave with a 45 degrees and the wave reflected by the crack. And the blue detector receives this reflected signal, and then we can find the crack in the whole pipeline. This whole device permanently performs this work to find a crack of the pipeline. Elastic wave tool is also very similar to the ultrasonic tool, but this method is usually used in the gas pipeline. In second figure, the two level links transmit ultrasound and detect an abnormal point. The detected points are recorded in a server or a device, and then a proper action will be performed by engineer or owner or other inspectors. Data loss and crack detection tools are very similar methods. One thing we should remember is selecting a proper method by considering the characteristics of pipes. This slide presents two other internal inspection methods. Strictly speaking, these methods are not internal inspection methods, but these methods support internal inspection methods. First, geometric inspection is gathering information about the physical shape or geometric of pipe. These tools identify any possible obstruction in the pipe, and it compounds a pre-passage of any other tools. Another supporting method is a mapping method. By using GPS, actual geographic coordinates of pipeline routes are calculated. As the same as geometric inspection, this method is usually used with other internal inspection methods. This slide explains hydrostatic testing. This method is a very interesting method because it requires a huge device and lots of water or liquid. This method tests the pressure carrying capacity of a pipeline. Before operation or during inspection or after repair, an engineer always wants to know whether an installed pipe works well or not. In this case, the hydrostatic test is performed. This test is a kind of full-size case study test, but this method cannot provide information about the extent or severity of the remaining damage. The method explained finally is direct method. Current internal inspection technologies or hydrostatic testing may be not stable or cost-effective on certain transmission systems. This method uses various above-ground surveys and prior experience to predict where corrosion will or may occur, and then field measurement and monitoring are undertaken to determine the condition of pipe at this site. This method can be divided into three. First, external corrosion direct assessment. Second, internal corrosion direct assessment. Third, stress corrosion cracking direct assessment. Generally, two or more tools are recommended in implementing a direct assessment program. Summarizing this section, the current state of art in oil and gas pipeline inspection technologies have provided data necessary to develop a rational, cost-effective strategy for pipeline management. Again, the selecting a proper method for inspecting oil and gas pipeline depends on the condition of the actual pipeline in question. This section will deal with non-destructive inspection tools for utility piping. Many methods for inspecting pipe can be adapted for use on an exposed pipe exterior. However, the non-destructive inspection tools can be deployed within the buried pipes. Considering there are so many pipes under the ground, this method is important. Although this method is usually used to inspecting a buried pipe, we should remember that these inspection tools are not applicable to all types of underground piping systems. There are so many non-destructive methods. We investigate them starting from a visual inspection. In this slide, there are three figures about CCTV and laser-based scanning and zoom camera. CCTV and zoom camera method use a camera and get a picture or a video. An inspector installs or puts a camera into a pipe and they analyze a situation by using a picture or video. Photographic and the laser-based scanning method transmit a laser into the wall or surface and organize three-dimensional high-resolution images. All these methods have different approaches, but they are performed based on the imaging or video. The external pipe geometric measurement provide only exterior information. An internal diameter and each condition of a pipe are more important because the capacity and its reliability can be determined by them. Laser-based geometric measurement method uses both a laser device and a camera. In this figure, a laser is distributed by a meter. Then a camera captures the distributed laser and calculates the diameter or the condition. Laser-based geometric measurement method is popular because it provides the ability to track the gradual deformation of pipe over time. Sonar inspection method is performed at the same principle of laser-based geometric method, but the laser is largely affected by liquids such as water, so that in water-filled pipes such as just water pipe or oil pipe, sonar is used to replace a laser. In this slide, we can conclude it. Even a same pipe, inspection method should be changed by content of a pipe. Onto this slide, we focus on the condition of internal space of a pipe, but there are outside factors affecting conditions of a pipe. Once pipes have been installed in the soil, they are typically constrained to move and settle with the soil or start to deform. Likewise, pipes can be affected by poor bedding conditions outside of the pipe. In this situation, External pipe bedding condition test is required. Some of the surface geometry techniques may be potentially find reasonably sized solid void. Similar methods already discussed in the chapter 4, so you should remember that method. Next, a significant proportion of damage to buried pipe comes from external mechanical damage caused by inadvertent and often unauthorized excavation around the pipe. This damage is not directly of interest to the current report, but detection of existing mechanical damage can be an important part of utility characterization. These techniques used for the mechanical damage detection of pipeline is already discussed in a previous section on oil and gas pipeline inspection. In this slide, two other piping scanning techniques are introduced. First method is ground penetrating radar. This method is similar to radar in an aircraft. A radar device transmits a signal, and the signal is reflected by a buried pipe, and radar device receives this reflected signal and make a map about the buried pipe system. The second method, infrared measurement. This method collects information about heat and make a kind of heat map. The uneven heating and cooling of a pipe wall or a pipe liner can indicate variation in pipe wall thickness and the bonding of a liner to the pipe wall or the presence of the solid void outside the pipe. These two methods can be applied during operation, but determining material type and other characteristics is usually not possible. Leakage and integrity are the main factors determining the quality of a pipe. In this slide, 6 pipe leakage and integrity testing will be introduced. The fundamental idea of these 6 methods is same. If there is a leak, there is a something abnormal response. First, smoking test is applied to section of storm or drainage systems to find leakage point, and it is relatively inexpensive, but it can have a poor success rate. Second method is a dye and trace testing. This method is performed to trace the connectivity of different pipe sections or leakage out of or into a pipe network. This method is typically more labor-intensive than smoking test, but it gives better and more verifiable result. The third method is pressure testing. In pressure testing, to find leaks more efficiently, the pipe network is typically tested section by section. It means by isolating the section under the test, from the test of the pipe network. The fourth method is acoustic and ultrasonic leak detection. This method involves listening for the noise of or noise and vibration that are emitted when a flow inside the pipe leaks through the pipe wall. The principle of this method is the abnormal noise or vibration should be detected. The fifth method is pipe wall conductivity scanning. The principle of this method is water leakage path through the pipe wall will greatly increase the conductance between the electron node inside the pipe and the buried electron node outside the pipe. The final method is very familiar to us. In gas detection, leaks in gas pipe can be detected by a chemical sensor. It is easy for overground pipe, but it is difficult to determine leaks for the underground pipes. As shown in this slide, there is no absolute method for leakage detection. Every method has its advantages and disadvantages. So, the consideration of the testing situation should be first performed. In this slide, I will introduce the importance of data and asset management system. The collected data should be incorporated in the data and asset management system. This information can be used in prediction of risk of failure and need for rehabilitation or replacement or establishing guidelines, standards, and regulations for pipe inspection and condition assessment. There are currently very few aspects of utility characterization data that can be reliably determined from a surface-based utility location or characterization survey. So this could change substantially with the introduction of smart marking or smart tagging system for utility. Currently, a wide range of tools have been designed and they are well developed for internal inspection, direct assessment, hydrostatic testing, and non-destructive inspection tools. The selection of a proper cost-effective method is still widely considered more art than science.